Hey everybody, this is Larry. This is me going over Q4 of the weekly contest 363, maximum element sum of a complete subset of indices. Hit the like button, hit the subscribe button, join me in Discord. Let me know what you think about this one. So I'm not gonna lie, this one I actually misread initially for a long time, mostly because I thought that the product of all the subset has to be a perfect square, not every pair. Because once I reread it as every pair, it became slightly easier, but not that much easier. I think the way that I would think about it is that in this problem, because you're trying to figure out the sum, it is always going to be greedy in some dimension. And what dimension is that? The dimension I'm talking about is that, let's say in this case, in the example 2 that they gave us, there are some possibilities, 1, 9, 1, 4, 9, right? And in this case, you always, like, because you're summing and all the numbers are positive, if not, then maybe you want to do some dynamic programming or something, or just take out the negatives, I guess, if you're doing a sum. So pretty straightforward still, to be honest, I think. But in this case, it is positive numbers, so you always want all the numbers, because why would you just do 1, 4 or 1, 9 if you have 1, 4, and 9, right? That's basically the idea. Yeah, so that's the first idea. Why does this work? Well, hopefully this is easy to understand, right? One series is going to be 1, 4, 9, 16, 25, 36, 49, ... And hopefully you see the pattern, which is that it is just x squared, right? This is 1 square, 2 square, 3 square, ... And of course, if you have 2 squares, you can easily see that if you multiply every 2 numbers in that series, you're going to get another square, right? Pretty basic stuff. Or I don't know if it's basic, but once you see it, it's hard to unsee. So I think it's just one of those things that, and you could kind of figure out why, right? Because 9 is 3 square, 16 is 4 square. So, you have 3 square plus 4 square. Times 4 square. Another way to write it, of course, is equal to 3 plus 4 square. So, yeah, right? So that's how you would do it, maybe. Did I mess this up? I think I messed it up. I meant 3 times 12 squared. Whoops. I am not... That's what I meant. By the way, this is going to be a square, right? So that's basically, how everything is in there. So then the question is, how do you get stuff other than that, right? So I was actually playing around with my notebook during the contest, and it turns out, and I think the way that I was initially thinking about it is with the number 2, right? How did I do it? The number 2 is obviously 2 to the 1. So to match it, you need 2 to the 3. So I was thinking something along those lines of like 2, 8, and then ... And then I was actually thinking about a pattern like 2 to the 3, 2 to the 5, 2 to the 7, for obvious reasons, because now 1 plus... To get a power, 1 plus 5 is going to be 6, 3 plus 5 is going to be 8, ... even power, it is a perfect square. So I was thinking about those lines, but of course this is not sufficient, right? Because here, you can actually add something, what did I write down? You can add something like 18, right? Because 18 now is still perfectly valid. 18 times 2 is going to be 36, and 36 obviously is 6 squared. And the reason behind this is just 2 to the 1. 18 is 2 to the 1 times 3 to the 2, right? And then that's when it kind of, it took a little bit more time, but that's when I kind of realized the pattern a little bit, is that this is actually 2 to the 1 times 2 to the 1 times 2 to the 2. This, and then 2 to the 1 times 4 to the 2, and so forth. Right? Yeah. Yeah. Right? So it's basically the pattern, and this is this times 1 to the second. So then now, and the reason is because now, given this 2, you literally, for every number behind it, there's only one component of that number, and it's going to be basically some I times x squared, right? So then now you have some I times some x squared, x sub, I don't know, this times another I times x of some other x squared. And of course, if you kind of just do the math, it's going to be I squared times, you know, and of course, this is going to be a square. So every number in this series is going to be a square. So that's basically it, is that we just kind of brute force on the I. And yeah, and I'll go over the code and we'll go over the proof as to why this is, or how this is fast enough in a second, right? So this is the code, this is the sequence, right? We start at 1, so we start at 1, we go 1 times 1 square, 1 times 2 square, 1 times 3 square, and we sum all of these because this is, like I said, this is greedy, right? We just sum up all the numbers that we can and we gobble it up. And then you do it for 2 and then 3 and then so forth. So what is the complexity of this, right? To be honest, there are some optimizations to be made. If you actually make some optimizations, I think this is actually would be linear. Because then you look at every cell once. I'm a little bit sloppy here because I don't make that optimization. And what I mean by the optimization, let's go to this. Let's actually analyze this without the optimization first, right? How do I optimize this without the optimization? Well, the idea here is that, you know, the first one's going to be 1, 4, 9, 16, 25, 36, The next one's going to be 2, 8, 18, 32, 50, 72, right? So, so the idea here for me is that I don't know the answer to this one, what the complexity is per se, or exact. I don't know the exact. Let's actually do this too as well. 12, 27. 54 is it? 58? No, 48. I cannot do math. 75. Right. So the thing that I thought in is during the contest, which is why I didn't make the optimization. I thought it would be fast enough. Is even though I don't know the exact complexity, what I can compare to is a similar idea, right? And a similar idea that I was comparing this to is the SIF. The SIF, of course, I always forget how to spell, of Aristoteles. Aristoteles? Okay, right? The SIF. And this is a prime SIF, which we don't use here. But if you kind of look at how it's done, and maybe, you know, you could skip this because we don't do that in the prime SIF, but that's only linear anyway, right? So if you do like a 2, 4, 6, 8, 6, 10, 12, and then you kind of do, right? Maybe we skip 4 in this case, but even if you do it, I think it's fine. Right? I know this is 16. But yeah, but if you kind of look at this, right, and you can, the idea I want you to kind of look at is that all these series, except for maybe the first one, all these numbers are strictly less than these numbers, right? So like, for example, if you kind of match them up, skipping the first one first, like these numbers are always bigger than these numbers. And what that means is that the SIF does more work than what we do, right? Because this just looks at more number. So that means that we look more. That means that the SIF is slower than what we do. And because the SIF, as you may know, the complexity is actually like n log n or something, right? So that means that our algorithm is going to be better than n log n, right? So that's that's basically it. Yeah. So that's basically the idea that I was thinking during the contest. And so this is how I know that this is going to be fast enough, because I know that this is less than n log n. It's much, I don't know if it's much faster, but it is definitely slower than, or faster than n log n, because this increases slower than the SIF, right? So that's basically why I think this is, the upper bound is going to be n log n, and this is why I'm fast enough. So how do you do this in linear time? I think the linear optimization is actually just almost like the same way that you do the idea of here, and I didn't think of this during the contest, to be honest, I just thought of it now, is that, well, it's just like dynamic programming, right? Or maybe even, because every every number, the next number after it is deterministic, right? Meaning that if the number is 4, the next number is always going to be 9, no matter what. Because otherwise, then you just combine them into more, right? So in this case, this is actually 4, 9, 16, 25, 36, ... right? Because, and this, of course, if this is the beginning, is a substring or subsequence, or, well, substring, well, both, I guess, subarray and subsequence of this, right? And of course, because we're doing greedy here, this is all going to be, you know, like this will always be not as good as this one. So we can actually just skip it. And if we skip stuff like this, and we skip every number, that means that the only time we look at a number is we only look at each number once or twice, if you want to say the beginning, you know, the quick check in the beginning to see if we've done it already. So every number only gets looked at constant number of time. So this is going to be linear time. So yeah, I think that's right. If I'm wrong, then I apologize. But yeah, but that's basically the whole idea behind this problem. And yeah. And keeping in mind that, I think one more observation of why this is linear, and you may wonder why, like, hey, if this is linear, then why is this not linear? Well, the reason is because each number can be looked at multiple times. For example, 12 is actually in 2 sequences, right? Or in this case, actually even 3, but we'll skip the 4, right? And of course, there's, 4 and 6, they're not the same sequences, but where here, that is not the case, right? Every number will only appear in one sequence if you skip them, because you can just kind of break it down by the prime factorization and kind of figure it out that way. And everything will be unique by some like diagonalization thing, I think. Don't hold me to it. Definitely, let me know in the comments if you've done it that way. But yeah, yeah, that's all I have for this one. Let me know what you think. This is linear time. I think constant space. I mean, the way I see it. Oh, yeah, constant space. I don't manipulate this. So yeah, that's all I have. Yeah, stay good. And you could watch me solve it live during the contest next. Though a lot of it, to be honest, I kind of wrote it on my notebook, so I don't know. But yeah, let me know what you think. Boop. This is dominating. Skipped ahead. Maybe I should skip ahead real quick. I mean, more people got Q4, so let's look at this first. One index array of every product of every pair of its elements is a perfect square. One and four. What? Is it one? Why do they switch from one index and 0 index? Okay. What does this mean? 8 plus 5 is 13. 16. Okay. What? The product of every pair of its elements is a perfect square. One and 4. Is it just the indexes? I don't get it. So we only care about indexes. It's very confusing. And then we're trying to maximize this. Okay. So then now, what am I doing? I have 1, 4. Okay, so what are the squares? So 1, 2, 4. No, 16. 25 is 5 and 5. So the only thing is just powers of 2s and powers of, well, 6 I guess is going to be a little bit different. Okay. People got this that quickly. People are smart. I feel like this is more tractable. I just have to figure it out. Okay. 10 to the 4. What is 10 to the 4 again? 10,000. Also corresponding as well. They just kind of copy and paste it. How many primes are there? Primes under 10,000. How many are there? How many primes under 10,000? 1229. Basically, is to do that. Okay, this one, which we always run one. Because you can add 1 to anything, like even 128, right? I don't know why 128 is not there, but am I understand it? Did I misunderstood this one? 1 times 2 times. Oh, every pair, not the product. Okay. So then, what does that mean? Right. So that means that there's 2 and then 2 times 3. Oh man, I misread this one. Okay. And then so every pair, all the products are not the same. Can I do a breakfast search? So it's 1419. Now that said, it's going to be too big. How do I do it? Well, a lot of people getting it. A lot of people getting that's this one, so I'm just going to get dominated today. Okay, every pair of its element, right? So what does that mean if I do TP? So if this is a square, then it has to visit a square, right? If not, then so for example, 8 would visit 2, but going backwards, let's see, right? You have 2 to the 3rd, which is the same, so not that. So 4 or 5, 2 to the 5th, but you also have 2 times, like 2 times 3 square or something like this. So like 18 would go with 8, right? What's 18 times 8? Just to make sure. Oh yeah, 144. And how do you do that? 100 to the 4th is going to be 10 or 100 square. So, wow, this is not great. Does this prime factorization even help me? Okay. Say 16, right? So 16 is going to be 1 and 16. it goes over n, so that's not very helpful. Man, I just don't know. Today is just not a good day, I suppose. 2 and 8, but no 1. Okay, so what does 16 look like? But the thing is, you can't even iterate for that because what are the patterns? It's 1 and 9, 2 and 8. It's always going to be the same things, right? 1 4, 1 9, 2 8, 4 9, 1 4 9, and then 1 4 9 is always going to be bigger, so then you can actually extend this. And that already eliminates some of the stuff. So you skip 1 9 and 4 9, so you have 1 4 9, and then you have 2 8, and then I guess you do some sort of DP on that. And then what's the next one? 16, I guess, and the one that requires all the stuff. Right, and that obviously is better than 1 and 16. About the 2 8 thing. The 2 8 thing is a little trickier, right? And then now you also have to deal with this is 2 to the 1, 2 to the 3rd, 2 to the 5th, maybe, I guess. So now this is times by 4, so 36. Right, so yeah, x and x squared, so that's maybe a case, I don't know. And then there's just 2 to the odd x, which is a weird thing. And then now you have 3, and you have 3 and 27 and dot dot dot. Right? I mean, this feels like Siffy, but I don't know if this is good enough though to get all the possibilities. Like, is there 3 to 36 one? No, because 36 is how did I even get 36? I just missed that. No, it's 32, Larry. 32. You can't do math. Okay, fine. 2 to the 5th is 32, not 36. Okay. But 36 is probably a thing. Because then you have 4, and just 2 to the 2nd. 4 to the 1, and then 4 to the 3rd, maybe. So that is 16, 64. Is that right though? I mean, it's right, but it doesn't consider stuff like how do you do 8 and 18, right? 8 and 18 would be a possible answer, but the way that we're doing our progression, it is not. And even this 3, you could even say 3 times 4, which is 3 times 4 is 12. So yeah, 3, 12, 27 would still be good, right? Because 36 and 27 times 12 is 18 squared. Right, so we're definitely missing some stuff if we just do it this way. Furthermore, is there a set in which this doesn't make sense? X squared has to be, no it doesn't, does it? No, X squared has to be by itself or in a thing. Yeah. You have to look at all the other. I just don't know anything today. This is going to be a disaster of a contest. Wow, people are really smart. Whew, yikes. So, all the square ones has to be with other squares. Okay. What about all the non-square ones? We have 2 and 8 and 32, say dot dot dot, but you can also even add 9 to it. Right. So it's 2 times all these things. It will still be good. So then it's 1, 4, 9, 16, and then 2 times all these, so it's like 2, 8, 18, and 32. And that would also be good. There's so many possibilities. I don't get it. Times everything by 3, so that's 3, 12, 27. Is that it? Maybe it is. Maybe that's the pattern. I don't know. And I don't know the answer to this one, so. Okay, what would that look like? So it's just 100 things, right? Is that true though? Because you can have 6, right? 6 is. And this is our pattern, but I feel like there's also it doesn't tell you what n is equal to 1 mean. I don't know that. I know the answer without it. What am I doing? What if you start with 6, right? Because you have 6 and then that's 2 times 3. That's 6 and that's 2 squared times 3 squared. Is that 36? So another 36 squared. But but that's a thing, right? So 36 square, but that's not going to be in our thing. Oh wait, yeah, is it? Because it's going to be 6 and then 24, 36. No, that's not 36. 54, and then eventually, maybe. Yeah, okay, fine. I don't even know what the answer is with n is equal to 1. I guess this is equal to max of nums, just one index number. Because technically every pair is a perfect square, right? I don't know if that's true, so we'll see. Current 0 to 1, right? While right, and then press is equal to max press of total, right? And then now we have to do another loop of right, and then now we start in something like this, but I might have to do some optimization. It's not even right. It's not right because I have to reset this. 14, 13. Why? How did I get 14? Oh, this is one index. I have to do a -1. Okay, fine. And so this is going to be equal to, okay, fine. 13, 19. Yeah, that's still wrong. Why? What am I getting 13 for? So from 0, this. Oh, this doesn't do anything, does it? It should be something like this, say. Okay, well. At least that's kind of good, maybe. We want 1 and 2 and 8. So why is that? So this should be current is equal to. Oh, this is no. What are you doing? Well, I guess 1 times that is true, but 2 and 8, right? Index 2. Oh, index 2 is this. I hate you when you're 0 indexing. 0 is going to be 1. We want 1. We want. It's not even right. Right. Okay, 1 and 4. 1 and 4 is 13, okay. What is 1? 1 is 5, which is really wrong. Oh no, this is. Okay, let's just do this for now. Okay. Okay. Is this right though? I don't know. Is this too much work? No, I mean the later one should work. Let's just YOLO some. Thanks for watching. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this problem. Stay good, stay healthy to good mental health. I'll see y'all later and take care. Bye bye.